In this video, we're going to talk about the common shorthand way that we represent the physical setup of an electrochemical cell. So in the last video, I drew this kind of big complicated picture, but we actually have a method for representing that whole setup in a single line of text that you can just type. So that is what we're looking to do here. So our line notation for electrochemical cells represents our physical cell setup, and that's important, not just the reaction, because we could also write our reaction in a single line of text that we can type. This is representing something slightly different. Often pretty much the same, but not always. More on that soon. So it represents our physical cell setup in a single line of text. So there are quite a few little intricacies to the formatting that I'm going to just spell out in an example. But the general gist of line notation is that we list the anode half reaction first, reactants and then products. Then we list the cathode half reaction. Again, reactants and then products. So I'm going to write out an example of line notation and then kind of pick it apart and show you what all of the different parts and pieces and symbols mean. So here we go. So this is a pretty simple example of line notation. So our anode is listed first, our cathode is listed second, and the dividing line between them is this double vertical. So this double vertical line separates our anode and our cathode. Effectively, it represents the salt bridge, is how I like to think of it. So that is telling us that everything to the left is involved in my anode reaction. Everything to the right of that double vertical line is involved in my cathode half reaction. So this must be the reactant. This must be the product. On the cathode side, the copper 2 must be my reactant. The copper solid must be my product, since I always do reactant and product first, reactant, then product, sorry, within a half cell. So note that we're not including the electrons here. It is just assumed that whatever electrons need to transfer are transferred. We are interested in the actual whole atoms that are reactants and products. So our single vertical line represents substances that are in the same container, so they're in physical contact with one another, but in different states of matter. So these two substances, the aluminum and the aluminum 3+, are both in my anode. They're in the same container, but one of them is a solid and the other one is aqueous, so we divide them with this single vertical line. For the same state of matter in the same container, we use a comma instead. So if these were both aqueous, this would be a comma instead of that single vertical line. So let's see, what else have we got? You'll also notice that I have included concentrations for my aqueous things here. We typically only include the concentration if it's not standard. So our standard concentration is 1 molar. So in this type of notation, if you don't specify a concentration, you can assume it's 1 molar. If it's not 1 molar, ideally it should be specified. So we can specify non-standard concentrations. You can specify 1 molar as well, and that's totally fine. It's just not necessary. So we can specify non-standard concentrations for aqueous things along with our state of matter there. So one thing to note is that if you have done your line notation correctly, you should find that the very first thing and the very last thing are both solids, are your electrodes. What color haven't I used? Sure, we'll go for red. So your line notation should always start and end with a solid. Specifically a solid metal, as those are the actual physical electrodes that are conducting electricity into your solution. If your reaction, if a half reaction doesn't involve a metal, you need to stick something in there. And this is where it's important to recognize that the line notation is representing the physical setup and not just the chemistry. The chemistry is an important part of that, but we're actually representing more than just the reaction. Because if your half reaction doesn't involve a metal, we need to add some piece of non-reactive metal just to conduct electricity. That we need some way for electrons to get into that solution or leave that solution, depending on whether it's the cathode or the anode. So if there's no metal involved, no solid metal involved in your half reaction, you literally just stick an extra piece on the end. So most commonly, either platinum or palladium are good choices. Of those two, platinum is actually the cheaper one, so it is therefore the more commonly used one, but those two things are both pretty common. So let's look at one additional example. That I'm going to have you guys try on your own based on what we've talked about. So I would like you to write the line notation for a cell that contains the following reaction. 2 copper 2 plus solid iron forms 2 copper 1 and 1 iron 2. So we'll say that all of our concentrations are standard for this one. We won't worry about that. But what you will need to do is identify what is the reaction happening at the anode, what is the reaction happening at the cathode, in order to be able to write your line notation. So pause here, take a moment and do that now. So in this reaction, we can see that copper 2 is being reduced to copper 1. Reduction occurs at the cathode, and iron is being oxidized to iron 2, so oxidation occurs at the anode. So that means that our cathode reaction is going to be copper 2 producing copper 1. It doesn't matter too much, but it is preferable to think with your reaction coefficients in lowest terms. We do not typically include coefficients as part of the line notation, so sometimes that can be a little bit confusing, but we just need the identity of the reactants and products. And then for our anode reaction, we will have iron reacting to form iron 2 and 2 electrons. So in writing our line notation, we want to start with the anode first. So we're going to start with our anode reaction and list our reactant first, which is the iron solid, followed by our product, which is the iron 2 plus aqueous. Remember that we do not include electrons. We will need to separate these by a single vertical line. Do note that these are vertical. It's not a forward slash, it's not a backslash, it is perfectly vertical. And we use that vertical line since they are in different states of matter. With that, we are finished with our anode. So these two pieces are our anode reaction. Our cathode reaction has copper 2 reacting to form copper 1. Both of these are aqueous. They're in the same state of matter in the same container. So this is where we use a comma to separate these two things instead of that single vertical line. So these are the reactant and product of my cathode reaction, but you will notice that there is no solid metal here. So this is one of those cases where we need to add something else in extra in order to make this work. So it doesn't really matter which metal you choose. Platinum is the most common one, so that's what I'll go with. It's a different state of matter, so we use a single vertical line and just throw that platinum on the end as something in there that will not react, but will allow this system to conduct electricity into the cathode container.